My name is Leon Chao. I'm from NIST, mechanical engineer working on Kibble balance technology. And my talk today is titled Two Tabletop Instruments Aimed for Commercialization to Realize Mass and Torque based on the Kibble principle. So first off, I'd like to introduce you to our PREEM team. PREEM stands for Precision Electromechanical Experiments, and we're comprised of physicists, electrical, mechanical, and optical engineers. And this picture is to me is a little humorous. It's kind of funny because in the middle we have our cartel boss Dave Newell, who sits here in the front, flashing his arm tattoo of his code data fundamental constants. Of course, as we all know very well by now, in 2019, this huge paradigm shift occurred for the entire world where the International System of Units, or the SI, transitioned from a group of 7 base units to 7 fundamental constants. And as Stuart and Richard explained already, the kilogram definition is now defined by a fixed value of the Planck constant. So this seems a bit nebulous, but the implications of such a redefinition are actually very far-reaching, and in my opinion, truly democratizes the SI. The numbers on the napkin here in this photograph on the right were our team's bar bets on what the final value of the Planck constant would be before the redefinition. And this was jotted down during a happy hour session across the street at a restaurant called Dogfish Head. So if you guys are ever in town, if you guys are ever visiting NIST in Gaithersburg, I definitely recommend you take a trip to Dogfish Head for a meal and a beer. So again, how do you make this connection between a rock with a mass of 1 kilogram to the Planck constant? Well, one way would be through something called the Kibble balance, which Richard already went into great detail describing the theory. So I'll spare everyone another deep dive, but but kind of just to drive home this concept, let's go through a short recap. So on the left, what we call force mode. Here we have the weight of an object, which is mass times the local acceleration of gravity, is counteracted by an electromagnetic force, an upwards force generated by pumping electrical current through a coil that is immersed in a radial magnetic field, described by B times L times I. So this is actually precisely how a commercial mass comparator works, but except in a mass comparator, the user needs to use a weight or a calibrated mass to define the BLI, whereas in a Kibble balance, it's inherently self-calibrating. As in it can calibrate its own electromagnetic force generated to make a Kibble balance a primary realization of mass that is now traceable to the Planck constant via voltage and resistance standards. The self-calibration happens in velocity mode, which is depicted on the right, where the balance rotates or pivots or oscillates, and the now electrically open coil sweeps through the same magnetic field as in force mode at a known velocity to induce a voltage. So by measuring this induced voltage and measuring the velocity, one can determine this BL calibration factor, which then gets ported back over to force mode. And and magically, voila, the pieces of the puzzle have come together to measure mass without needing to compare it against another mass. So this is how everything works in a nutshell. So here's an image of our NIST-4 Kibble balance, and after 2019 is capable of realizing kilogram level masses to 8 decimal places. That's basically being able to detect the mass of a fingerprint left behind on the shiny surface of the artifact being measured. So presently, this machine here serves as the primary mass standard of the US. And what you see here is with the giant vacuum dome removed. And this instrument stands well over 2 meters tall. And just by looking at this photo, right, you can tell it's really complicated because to get to 8 decimal places, you need everything that Richard was talking about earlier, right? You need the high vacuum environment, you need gravity, local gravity measurements, robotic mass transfer system, a rack full of electronics, at least for us, that is as tall as the balance itself, and is tied to two quantum electrical standards, right? The PJVS and the QHR, the voltage and the resistance, quantum resistance. And these two devices, as we heard earlier, are where the Planck balance, sorry, the Planck constant is buried in. So even though we are humble scientists, NIST is still an American institute, and as Americans, we love to obnoxiously boast about the things we do. So leading up to the redefinition of the SI, there was quite a lot of coverage of the redefinition of the kilogram in the press, ranging from Popular Mechanics to the New York Times. But anyway, the highest honors, which I think is kind of funny, are shared with our Kibble balance, making it on the cover of Physics Today, and Smithsonian Magazine listing it as one of the top 10 scientific discoveries of the decade, alongside CERN's first detection of the Higgs boson. And this article came with this very interesting image showcasing our Kibble balance, or at the time it was called the Watt balance, at the center of the picture. So the publicity really permeated and all the way through TV, radio, and internet. So NPR hosted a podcast with John Pratt on the kilogram redefinition. Samantha B from TBS did a segment. Twitter had a bunch of retweets showing pictures of Stefan, John, and Dave's Planck constant tattoos. And the YouTube channel Veritasium shot a video on NIST4, which garnered, millions of views. PBS filmed an hour-long documentary called The Last Artifact. So this concludes my shameless boasting, but I put this out here because I think each one of these individual pieces of media is very, very fun to watch, very, very interesting, and brings metrology as a whole into the limelight. So I encourage you guys to go hunt for these things. Now to prove the power of the new quantum SI, our team has been demonstrating the scaling advantages and opportunities associated with this redefinition. So mass is no longer traceable to a single kilogram artifact that's locked away in a vault on the outskirts of Paris, and now can be directly realized, right, in terms of electrical units. So top left is the NIST4 Kibble balance, which you've heard about already. And in an effort to cover an expanded range, for example, 500 milligrams up to 20 grams, we've built tabletop Kibble balances, which can do this with uncertainties on the order of parts 10 to the 6. And we want to ultimately evolve these things towards commercialization. So everyone has this technology right in their own labs. The Lego Kibble balance was built for educational outreach purposes, but can actually measure gram level masses to about 1% if you set it up properly. QEMS, QEMMS, is currently being built as a smaller sibling to NIST4, also as an NMI lab grade instrument, aiming for 100-gram measurements with parts 10 to the 8 uncertainty. So also we're involved with FOMO, which is using the Kibble principle for in situ laser power calibration via photon momentum transfer. And this is also directly traceable to the new SI. Torque realization using the Kibble principle is also under development, ultimately aiming for commercialization, just like the tabletop balance. And U.S. Department of Defense have kickstarted us with 3-year-long funding for both torque and tabletop Kibble balance development. And hopefully these commercially viable versions of these technologies will help modernize and streamline the calibration processes around the country. And finally, we have the venerable grandfather of all scientific balances, which is the torsion balance. And this is used to measure the Newtonian gravitational constant, which we call big G, which governs the dynamics of the celestial bodies in our universe. So here's the present state of mass dissemination in the US. So say you're a mass metrologist and you want to use a 1 gram calibration weight to calibrate your analytical balance or your mass comparator. How do you know your 1 gram mass is actually 1 gram? Well, in principle, it starts with your shipping your mass set, which around here ranges from 1 milligram up to 20 kilograms. So there's this big wooden box that weighs over 40 kilograms total, and you have to ship this to NIST. So on our end, we start with the top of the traceability chain using the NIST 4 Kibble balance. And then this instrument assigns value to the kilogram artifact with about 10 parts per billion uncertainty. This kilogram is then handed over to another team, and at NIST they're called the Mass and Force Group. And these guys do a series of inner comparisons and subdivisions with an arsenal of commercial mass comparators to scale down from 1 kilogram all the way down to 1 gram. So this process takes about 1 week to complete, and you need 44 weighings, 1,200 individual measurements, and then your final uncertainty has increased by 2 orders of magnitude. The 1 gram mass is then placed back into the crate, and then this 40 kilogram carton is shipped back to you, at which point then you can use these masses once again to calibrate your comparators. And over time, you start losing trust in your mass values because you dropped it one too many times, you coughed on it, and so you have to then ultimately send it back to NIST for recalibration, which is costing you more time and more money. So what if you could cut out this convoluted mass traceability chain? Right. So we introduced this idea of a commercial tabletop Kibble balance designed for private industry. So a modernization of mass metrology such as this would be able to take full advantage of the new SI, which severely truncates the traceability chain. You could essentially realize your gram level working standards to ppm uncertainty on one side of the lab, and then walk over to the other end and use it to calibrate your analytical balances. Or even better yet, you can just calibrate your customer masses directly on the tabletop Kibble balance. So of course, the traceability chain shifts from mass metrology to electrical metrology, which we already know has a very strong infrastructure in most primary calibration labs anyway. So if we zoom out a bit, this general concept of developing tech that directly supports and empowers private sector metrology not only aids in increasing the autonomy of commercial labs, but helps evolve us at NIST from a primary calibration lab to more of an advisory board, so to say, on how to capitalize on the benefits of the new SI. So here's our first generation tabletop Kibble balance, which we've named KibG1, which can realize gram level masses to 6 decimal places. So if you look at the photo, there's a one kilogram stainless steel mass next to it, and this is just for scale, so you know approximately how big this instrument is. In the middle is a CAD rendering of the critical components, and to the right are snippets of data and our overall uncertainty budget from our Metrologia publication. Some of the key features include using a square cross-section air bearing as our linear guidance mechanism. And this is an air bearing, so it has virtually zero friction. We use a dual coil and single Sumerian cobalt magnet system. And then at the top, we have a truncated wheel which pivots about a knife edge. Our position sensing is done by a home-built heterodyne interferometer using a Siemens split helium neon laser as the source. So all in all, we showed this proof of concept instrument could, hold its ground against the traditional OIML class E2 gram level artifact masses at single digit ppm level uncertainties. But even though this thing is functional, it's visually uh, not very appealing, right? It's still complex and it looks just too much like what it is, which is a lab experiment. So we didn't think too much of this after we developed it. It was kind of almost like a side project in NIST 4. But somehow the U.S. Department of Defense and specifically the U.S. Army Metrology Lab found this and then approached us, signaling to us that they were ready to be the early adopters of Kibble balance technology to modernize and future-proof their mass metrology infrastructure. Since they spend well over $1 million annually just on the logistics of shipping these masses around the country back and forth. So the Army expressed their ultimate vision, which years from now would be that all mass comparators would be replaced by Kibble balances. And after multiple meetings, I think it's almost safe to say that this is now an entire Department of Defense wide vision, with our largest advocate now actually being the Air Force. So about a year ago, the Army and NIST, we began a 3-year-long collaboration to develop the second generation tabletop Kibble balance. And so far, we've built a prototype, which you can see here. It's much smaller and much simpler than its predecessor, with huge design focuses on using off-the-shelf parts and user friendliness. So for example, the mechanical guidance mechanism is now a flexure-based system, which decreases the size and increases robustness compared to the air bearing from Kib G1. The electromagnets are now commercial voice coil actuators instead of these home-built custom machined systems. And we're currently investigating using a simpler, more cost-effective method for optical displacement sensing. Here are some pretty recent photos of Kib G2, which is our second generation balance, as we continue to work on it. On the left here is our guest researcher, Tapelo from National Metrology Institute of South Africa. He's carefully placing this 2-gram mass on the mass pan. On the right is a close-up view showing the optics currently mounted to the system, and we're basically conducting a comparison of an optical encoder against the accuracy of an interferometer to see if it's feasible to shift over to an optical encoder. So with every iteration of Kibble balances, they seem to shrink in size and complexity. Perhaps the biggest leap was from NIST 4 to the Lego balance. And in hindsight, we should rename the Lego Kibble balance as Kib G0, because in many ways it was the catalyst for all these tabletop experiments. And as NIST, our wheelhouse is designing custom metrology experiments, and we recognize that we know nearly nothing about how to get this technology into the hands of consumers or end users. So taking guidance from the DoD, we've tried to remedy this by searching for an external partner with a precision balance manufacturing company. So in recent news, we are very, very close to finalizing a collaboration contract with a very well-known precision balance company. You guys can probably guess who, but I don't think I'm allowed to legally disclose this yet. And if anyone here attending has, a similar a vision of modernizing your country's mass metrology infrastructure with commercial capabilities, please let me know. So far, the DoD labs across the U.S. Have voiced to this company that we are collaborating with that they are patiently waiting in line to purchase potentially, hundreds of units, which actually helps our case in proving that there is indeed a market for this stuff domestically. So if we can showcase that there's actually international interest in owning such primary mass standards aimed for calibrations labs, this would really help our case in securing resources and pushing and continuing this momentum and pushing this idea forward. So basically, more people that express interest equals more resources that can be devoted towards developing this next generation system. All right, so what about torque? Torque, as we know, is defined as the perpendicular component of a force applied to a lever arm. So like wrenches and screwdrivers apply torque to fasteners, like screws, nuts, and bolts. And in everyday life, we actually don't care too much about applying the correct amount of torque to fasteners. It's usually tight enough so your chair doesn't fall apart or collapse. But things are quite different when you start building things like $80 million fighter jets, which undergo enormous dynamic stresses and strains. So if these fasteners are not tightened to just the right level of torque, it could mean catastrophic failure. And how do you ensure that these thousands of screws and bolts on the aircraft are tightened correctly? Well, you need torque wrenches and torque screwdrivers that undergo regular calibration. So around the same time as when the U.S. Army collaboration on the Kibble balance began, the U.S. Air Force began funding us for 3 years to develop an absolute torque realizer, also based off of the Kibble principle, for directly realizing a 0.1 to 142 inch-ounce force with an uncertainty of 0.1%. For directly calibrating sensitive torque watches, screwdrivers, and wrenches. So I know that these are extremely, extremely bizarre units that we're not used to seeing, but it's because the U.S. is allergic to real units. I'm just kidding. This is because the torque industry domestically uses these units historically, so we're kind of stuck speaking this lingo with them. But I have the real units in parentheses underneath. So the ultimate goal of this project is to design a prototype that is user-friendly, accurate, and robust enough to ultimately evolve into a commercial product. So to give you an idea of the lowest torque we're trying to measure at 0.1 inch-ounce force, it's like trying to detect the weight of a small honeybee at the end of a meter stick. So on top of that, we need to know this torque to plus minus one of its wings. For us, this is a super fun challenge to learn what the lowest achievable limit is for our first prototype. And for the Air Force, we can only imagine what kind of top secret Area 51 alien spacecraft stuff requires precision torques to this level. So currently there are two main testing or calibration processes for torque tools. The first method is for mid and high ranges, where a torque tool such as a torque wrench is set to the desired torque value and oriented such that its drive end interacts with a torque transducer. Which is a torque transducer typically is comprised of a couple of strain gauges, calibrated strain gauges internally. Then either the transducer or the torque tool are rotated until the tool clicks, right? This click is then detected by the measurement system, and the torque measured by the transducer is displayed. If the torque value that's measured by the system is within tolerance, the tool passes verification and everyone's happy. If not, and this is kind of wasteful, right? They typically just chuck or discard the tool, uh, and sometimes they'll adjust it back to be within tolerance. So these transducers, they can get pretty low, but nothing exists on the market right now below 1 inch ounce force at a quarter of a percent uncertainty, or 0.25% uncertainty. So these these are all considered transfer standards as well, and none of these are primary, as you need frequent calibrations against mass and length. Um, so the second method is based off of the purest definition of torque, using literally sticks and stones by suspending a calibrated mass at the end of a calibrated lever arm. So the image on the right shows a commercial truncated wheel with commercial masses suspended from each side. This is common practice in calibrations labs for calibrating small torque transducers and torque tools. And for lower value torques, a torque tool is tested by using known mass and length values and simply hanging the mass off of a known lever arm, then reading the value displayed on the torque tool. So this can be kind of difficult, it's very finicky, time consuming, it's very inefficient, and still ultimately traceable to old school length and mass standards. So the current torque traceability chain is quite long, involving not one but two complicated chains for both mass and length. And at the end of the chain there, you see one kind of torque sensor used in calibration. So we want to cut out this convoluted traceability chain between quantum mass and length to end user torque sensors. And by the time the calibration chain reaches the torque tools from the primary standards, the uncertainty has been watered down by 1,000,000 times. So the idea is, just like with the tabletop Kibble balance, is to build some torque realization gizmo to replace this entire chain, which only needs to be accurate to 0.1% to outperform, everything that's currently out there. So our plan is to create a device that'll take us from this stuff to this, right? Some black box, or in this case, this blue box, that can directly interface with torque tools and give direct SI traceability to 0.1% uncertainty. So enter the enter, or the electronic NIST torque realizer. What you see in this photo is everything you need to build a primary torque standard traceable to the new quantum SI via electrical standards, just like a Kibble balance. And the end user can directly plug an analog torque watch, like you see here, to the enter to calibrate it. A pair of rare earth magnet rings generate the magnetic field and are mounted to a drive shaft and interact with a D-shaped coil, which is manufactured on a stack of printed circuit boards. And the current version of Enter rotates about a pair of very slick ceramic bearings, but its internal friction is what's limiting us from getting to that B on a meter stick level. We have plans to design version 2 using a rotary air bearing, which we've already acquired. The physics is generally the same as the Kibble balance, except in this time around it's converted to a rotational frame. And here are the scalar versions of the equations. I think I'm running short on time, so I'm going to skip over going through the math. But essentially, the plot here is of the magnet spinning 120 revolutions and fitting each revolution. And as you can see, that our calibration factor in this case is it's not BL but BL times R. Is well within this entire profile, is well within the uncertainty that we're shooting for. Here's our preliminary uncertainty budget. Our target is 0.1% or 1,000 ppm. And even when we fold in now the uncertainty of the mass and lever arm, which are the terms in red, which we use as a verification technique for checking our enter performance, we're still within the specs. And this was determined at 2 Newton millimeters. Okay, here's a comparison between two industry transfer standards against our primary standard. So Enter demonstrates that direct torque realization is possible, and at 0.1% is not very difficult to achieve, especially when it comes to truncating this, in my opinion, a very wasteful and long traceability chain. And I think Enter will aid the Air Force and hopefully the entire DoD and hopefully globally at some point um, in modernizing their torque metrology infrastructure. So for us, a provisional patent has already been submitted for the system, and we'll try to follow closely behind the progress of the tabletop kibble balance by beginning our search for a creative partner soon. So again, if you could see the benefits of this instrument helping in modernizing your country's torque traceability infrastructure, please let me know. If I can collect a list of countries or people that would potentially be clients, this would heavily aid in finding a collaboration with a private company to develop this commercial system. So with that, I like to just reinforce one more time that, at least in my opinion, the utility of the new SI should be widely available to everyone globally, and it empowers all metrologists to own affordable primary standards within their own walls. We're pushing very hard, as you can tell, to get Kibble Balance technology into the hands of calibration technicians and end users, starting with the tabletop Kibble Balance and electronic NIST torque realizer. So thanks for listening. I know I went a little over time.